Hello, today we shall look at the classification of polymers where we will look into the details of the molecular shape which is subclassified under molecular characteristics. So we have already seen polymers that can be classified in the following ways on the basis of origin, thermal response, type of polymerization. We have under molecular characteristics. The classification we have seen molecular weight as one of the ways in which they can be classified. So today we shall look into molecular shape. Polymer molecules are normally in on a piece of paper or in any books. We can see in two-dimensional on a in a two-dimensional plane. We see that the polymer molecules are shown as linear chains, but the backbone atoms are actually arranged in a zigzag fashion. The single chain bonds are able to rotate and bend in three dimensions. So as we know, if it is a single bond, that is their single chain, and then it is able to rotate and bend in three dimensions. The third chain atom can lie anywhere on the cone of revolution. As one can see, if it is just two atoms that are bound like this, two carbon atoms, say for example, then the third carbon atom can lie anywhere in this cone of revolution here. This dotted line, it can lie anywhere in the space. Subtending an angle of say 109 degrees with the adjacent atoms. Only in this case we can have a straight chain as shown here. So the carbon atoms are arranged in a linear fashion. If all these carbon atoms which are forming the backbone can subtend an angle of say 109 between each other, or they may also have bends in the chains, something like this. So this bending of the molecular chains leads to excessive intertwining and entanglement of neighboring chain molecules. Also, the end-to-end distance of the polymer chain is actually much smaller than the total chain length. So since they are bending, so what one can imagine is that because of the entanglement, etc., whatever the polymer chain length may actually be there, it may be the length may be large, but because of the bending, the end to end, the ends of this molecular chain may lie much closer than expected. So one can imagine this to be like say fibers that are there in a maybe sliver. So if they are more entangled, they would be the ends of those fibers are lying closer to each other because they are hooked or they are entangled in certain fashion. But if one were to straighten them, then the actual distance between the ends of the fiber can be seen that the length is larger. So one can imagine the molecular chains to be like fibers in a sliver. These random coils and molecular entanglements are the large elastic extensions displayed by the rubber materials. So, mostly in rubber materials, one will find that there are huge molecular chains that are entangled into random coils. Some of the mechanical and thermal characteristics of polymers are a function of the ability of these chain segments to experience rotation in response to applied stresses or thermal vibrations. So, some of the mechanical and thermal characteristics depend only on the fact that these molecular chains or segments are able to rotate once you apply some amount of say stress or maybe some thermal or some heating you apply, and then because of that, if the chain segments are able to move or rotate, then some of the mechanical and thermal characteristics would be depending on this ability of the chain segments to experience this kind of rotation or shifting. So rotational flexibility is dependent on the repeat unit structure and chemistry also. So this whether the molecular segments are able to rotate, or whether even they are able to, how flexible they are, will depend on the repeat unit structure as well as the chemistry of that repeat unit. For example, the region of a chain segment that has a double bond is rotationally rigid. So if there is a double bond in the chain segment somewhere, then in that case that molecular segment cannot rotate around itself or cannot shift or change. So it will remain more rigid in that way. Also, the introduction of a bulky or a large side group of atoms restricts rotational movement. For example, we shall look at polystyrene molecule, which has a phenyl side group, and they are more resistant to rotational motion. As we can see over here, the molecular structure of a repeat unit of polystyrene, where one can see a benzene ring over here, two carbon atoms and three hydrogen. And similarly, you will find that polyethylene, which is similar. The only difference is that instead of this ring over here, you will find another hydrogen atom over here. So because of this bulky or large side group of atoms that is there, it will restrict the rotation of this entire molecular segment around itself. So it will be more resistant to rotational motion. So with this, we come to the end of this lecture on the shape of the molecule. Thank you.